Good morning, everyone. Good morning, everyone. Today we have a webinar on charge and spin readout techniques in quantum dot qubits. I'm Shikha Mehrotra and I am honored to be your host for today's webinar. Before we dive into our topic, allow me to begin by sharing the profound impact that quantum computing has had on the landscape of technological innovation. It is a promising frontier that holds the potential to revolutionize how we approach some of the most complex challenges in science and technology. Quantum computing offers unprecedented computational capabilities, and its applications are as diverse as they are groundbreaking. Recognizing this potential, CDAC, a pioneer in high-performance computing, has embarked on a journey of exploration into quantum technologies. This journey is a natural progression from our long-standing expertise in HPC architectures. Today, we stand at the intersection of classical and quantum computing, leveraging our experience to drive innovation and bring quantum technologies closer to reality. In our quest to build a thriving quantum technology ecosystem in India, CDAC Bangalore proudly presents the Quantum Outreach Program. Through this initiative, we aim to create a platform for knowledge dissemination, collaboration, and education. We organize workshops, training programs, webinars, and other activities, all geared toward nurturing the quantum pioneers of tomorrow. As part of this endeavor, we have launched our flagship Quantum Outreach webinar series in collaboration with IEEE. These webinars aim to delve deep into critical topics related to quantum technologies and provide insights from the forefront of quantum research. Today, we are privileged to have with us an eminent expert in the field, someone who has dedicated their career to advancing our understanding of quantum phenomena. Our esteemed speaker, Dr. Madhu, an associate professor at the School of Physics, Indian Institute of Science, Education and Research, Thiruvananthapuram, brings a wealth of knowledge and experience. Dr. Thalakulam's journey in quantum physics, marked by academic excellence, includes a PhD from Rice University and postdoctoral fellowship at the University of Wisconsin-Madison and Sandia National Laboratories in Albuquerque. His research spans quantum dot spin qubits, quantum transport, quantum electrical sensing, and transport on 2D systems, offering profound insights into the quantum realm. Today, he will share his expertise with us, guiding us through the intricate world of quantum dot spin qubits and quantum transport, among other captivating topics. Now, as we proceed through the webinar, feel free to type your questions into the chat. We will do our best to address as many of them as possible during the question answer session. So without further ado, let's go started with the webinar. I'll now hand over to Dr. Madhu Thalakulam. Over to you, sir.
Thank you very much, the CDAC team and Shika for coordinating this event. And I'm really overwhelmed by the introduction. And I hope everything is audible and the screen is visible. And if there's anything, either message me or call me if there is any disruption. And all right, so I'm from IISER Thiruvananthapuram, and this work is actually most of the work that I'm going to discuss, some of the work that I'm going to discuss, made possible by the generous funding from various funding agencies. including the Department of Science and Technology, STARS program, SERB, and also from the institute. And let me very quickly go to give you an overview of what we do in our lab. This is just going to be like a 30-second, introduction. So we have 2 or 3 diverse fields, but all these involve, very sensitive transport measurements on low-dimensional systems, quantum dots or nanowires, or 2-dimensional systems. We have a project on mesoscopic electrical amplifiers to try to push the limit as much to the quantum limit. Most of the discussion will evolve around this today, but I'll be giving you an overview of the topic rather than going in detail, the technical details too much into this work. And there is another project which is funded by DST on quantum dot spin qubits, but these are kind of closely related. And there is another project on 2-dimensional superconducting systems and circuits funded by SERB. And we are also trying to understand and transfer this technology to other layered systems. That is also that's another ongoing project. So being said that, let us look into, let's walk into the topic, looking at the very basic, from the very basic understanding of electrical measurements. So that what we do generally, in layman languages, we measure either voltage, current, or resistance. And what you see here is a multimeter, which actually can measure a lot of parameters such as voltage, current, resistance, frequency, capacitance. And these are all related. Voltage is related through current and resistance. And these 3 are all interlinked, either by a division or a multiplication. But now the interesting fact is where is the charge? Okay. And our topic today is charge sensing. But if you take any of this multimeter, you will not see a knob position where you can turn that into measure some charge, which is not there. Okay. But if you look carefully, charge is probably the most fundamental electrical quantity among all this. And the new definition of on SI systems. Okay. So if you look at the outermost ones, like electronic charge, velocity of light, time structure constant, Planck's constant, Avogadro number, and Boltzmann's constant, and these are the most fundamental unit. And everything else now, since 2019, is actually defined in terms of these quantities. Okay, like everything else, mass, amperes, everything else, seconds, kilogram, whatever units that you can think of, everything else is now completely defined by these actually 6 quantity. Okay, and charge is one among them. And if you look at charge, is the only electrical quantity in that, and that is the most fundamental quantity. But we don't really do that measurement, on daily life, right? We measure mostly voltage, current, or resistance. Now, if you look at another quantum technology field, that is quantum electrical metrology, which we are also kind of walking into that. So if you look at, there are 3 fundamental quantities. One is the voltage, which is defined by Josephson voltage standard. It is a quantum phenomena. And the resistance, that is defined by quantum Hall resistance. But if you look at the current, the ampere, that is still lagging behind. If you look at compared to voltage or the resistance standards. If you look at the inner triangle here, there are only 2 constants here. One is a Planck's constant, one is electronic charge, right? There's nothing else. So everything else is defined in terms of that. And if you look at ampere is basically a certain number of electrons, going through circuit per second, right? Or coulomb per second, right? That is ampere, right? So now what we still need to, we are still limping behind the measurement of, accurate measurement of the charge. That is the issue. That's the problem. Okay. And what else can do if you measure charge? Here, this plot here shows electron transfer rate through a circuit, okay, until gigahertz, okay, and the corresponding current. And it's, of course, we know that it will be a straight line. And I have a dotted line here, which says typical current preamplifier noise floor. And most of the commercially available highly sensitive current preamplifier, the noise will be like a few femtoamps, 10 to 100 femtoampere range. That's what you are going to have, unless you have something very, very specialized equipment. It will be in that range. That actually correspond to, 1 ampere correspond to approximately 6 to 10 to the power 18 electrons going through per second, whereas 10 to 100 femtom is correspond approximately 10 kilohertz range, right? 10 kilohertz range, tens of kilohertz. But that is a transfer rate. If you look at that noise floor, what that means is if your transfer rate is slower, slower than that, if your tunnel rate through a circuit is lower than that, you cannot measure the current. That is not going to be work. So you actually need to detect charge. Okay. And of course, there are bandwidth issues and all other things are there. So that is what's giving you this noise floor here. Okay. So now the issue is current measurement is not going to be very successful when you have high impedance devices where the currents are lower. Okay. And that is the situation when you deal with most of the quantum electrical circuits. The currents are always going to be low. First of all, you cannot run really high current through it. Secondly, these are all high impedance devices. So the impedance is like mega ohms in the range or more when it's been the operating regime. So you cannot measure the current and understand the device characteristics. Okay. So one major application for measuring the charge, some quantum current standard. As I told in the couple of slides before, if you want to define a current, you actually need to count the electrons one by one. That's the actual way of defining a current. That's the most accurate way. Okay, so this is a circuit where the yellow regions are some kind of pumps. You can think of like it's a turnstile gates that you will see in a metro station. Okay, so only one electron can go at a time, just like one person can go at a time, just like one electron can go at a time. And these regions are some kind of single electron detectors. That means you actually can detect one electron at a time. Okay, and you can operate these gates, in tandem and periodically, and you can have electron go through this circuit one by one, and you can detect it and count it, and you can accurately make a current standard. That is the current, state of the art. I mean, that is where the world is going. And for that, what you would require is a highly sensitive charge sensor, not a current sensor, because you want to sense one electronic charge of one electron. It is minus 19 coulomb, right? That's what you need. It's a very small number. You don't think it's a large number. It's a very small number. Okay. And that is one major application. Another application actually comes from quantum dot qubit readout. This is something which I will explain a bit further. So the idea here is you have some electrons confined in certain region, and the spin state of the electron, whether spin up or spin down, you can encode your qubit states in that spin state. For example, spin down is 1 and spin up is 0. I mean, that depends on the system, G factor, work details. But one up spin is 1 and down spin is 0, or up spin is 0 and down spin is 1. But anyway, it doesn't matter. Okay. So that proposal came in 1998 when the art of the quantum dots, started, picking up. Okay, gated quantum dots. But now, since I mentioned the word quantum dot, I should tell you what is a quantum dot. Okay. Then what I will do is, then I will tell how we are going to sense these electrons in the quantum dot, how this will lead to qubit readout. Okay. That's how we will, the talk will go today. Okay. Now, quantum dots. Okay. Quantum dots are actually very small, submicron scale regions of charge confinement, especially electron confinement, and you can also say hole confinement, which is a semiconductor. Okay, and there are various ways to realize a quantum dot. In this, for example, there is chemistry way, or what we also call the bottom-up way. That is a colloidal quantum dot where it's a solution process. Okay, and you can get really nanoscale nanoparticles which are conducting, and this is bunch of nanoparticles dispersed on a some substrate, and it will have its own emission. I mean, when you shine light, and then there is another way, epitaxial. What that means is you actually make it a monitor beam epitaxy. So, but you basically grow islands of or puddles of regions which are conducting, and then these two are actually bottom up. Okay, because you're starting from atom through the into submicron scale region. So these are actually bottom up method. And there is another way, quantum dot. That means you remove material and confine a small electrons into a small conducting region. These three are actually mostly, I would say that these are physical confinement of electrons in a small region to define a quantum dot. Physically confined. Okay, you define boundary physically. But now you could also do by electrostatically, okay, because these are electrostatic objects. So what we do is it's a combination of both. You have some kind of a nanowire, then you put some gates, just like MOSFET technology. And when you apply voltages, electrons will get confined to a small region here. And this large region is the source. Another large region on the right side is the drain. And you can actually run current through this quantum dot. Okay, I mean, there's a small non-conducting region here that you can consider as a tunnel barrier where charge will tunnel from the source to the quantum dot and to the drain. Okay, so that is these are called gated quantum dots because you define the confinement and all the parameters by gating. And this is another example where you have nanowire. You can put more gates and you define a double quantum dot. So if you look at the fact about quantum dot is nothing but confined electrons. But we have a natural example of confined electron. Those are atoms. Okay. And because this is the confinement potential, this is a rough drawing of that. And you have discrete levels. And because of the discrete levels, you get all the atomic physics, all atomic properties such as emission, transition of electrons, all kinds of things. And if you combine two atoms, that becomes actually a molecule, I mean, diatomic molecule. And you can actually share these two atoms can actually share electrons. These are the molecular states. So if you look at carefully, here I have a confinement of electron, which is man-made. This is a natural confinement. So that's why this is called an artificial atom, often referred to as artificial atom, because this actually share a lot of properties and a lot of physics from the atomic physics field. Okay, and here this artificial molecule, this natural molecule, these two share a lot of common things, share a lot of physics. But interesting fact is you don't have much control over these properties here because interlevel spacing you have no control, and how much these two are coupled you have no control. There is some energetics works into it, some thermodynamics and some quantum physics works into it, and that is defined by nature. But here you can change everything by the electric field. For example, if I increase the voltage on this gate, I can make this tunnel barriers larger. I can actually make this well sharper, and this coupling I can change by changing the voltages on this gate. So this is actually completely tunable. All parameters, size, everything is tunable here. You have the tunable atom, whereas these natural atom and also these colloidal things are also kind of lacks tunability. This is not at all tunable, but here also it is once you get this dispersion of this material, that's it. You cannot do change its properties further. So that is interesting fact about these quantum dots. These are actually called gated quantum dots. Okay, because you define or confinement or the quantum confinement by electrostatic gating. And these gated quantum dots were actually proposed for hosting quantum information, okay, or qubits. So for example, if I take, this is just a representation of the quantum bell, and if I take the state here and apply magnetic field, I can Zeeman split these two states and I can define the spin up. These are spin states, spin up and spin down as two different distinct qubit state. And I can actually induce transition between these two by applying microwave pulses. By microwave, because energetics says that the difference approximately will be the microwave regime. Okay, this just like you can drive transition in a natural atom by laser. Here you are driving transition in an artificial atom by microwave. Physics is same. So these two states can be used to host the qubit states. And that is a proposal by Loos and DiVincenzo in 1998. So this approach is actually called LD qubit or Loos-DiVincenzo qubit. And later, another approach came, that is you use both quantum dots, and that's an artificial molecule. And this this molecular state can be a single state or a triplet state. There are 3 triplet states. But if you look at T0 triplet state and single state, they are pretty close in energy, except for the tunnel coupling. They are very close. If the tunnel coupling is more, the spacing will be more, but they are very similar, okay, in energy. So these two have different spin states also. So either you can use this as these two as qubit states, or these two are the qubit states. There are advantages and disadvantages for both of these architecture, both of approaches. Okay, but both of them are equally popular. So this is actually called ST0 qubit, single triplet qubit, and this is actually called LD qubit or Loos-DiVincenzo qubit. That is the current the terminology. Now, That is just one qubit, right? Now, just like in a natural, in our processor, you start with a FinFET and you define a processor. In a quantum processor, you actually start with the quantum dot that replaces your MOSFET in your, in your natural process, in your classical processor, and you have an architecture eventually, and each of the state. Finally, after you do the computation, a chain of an algorithm, and you will end up with states for this for a spin eventually, whether it is a single triplet qubit or your LD qubit, you will end up with a state. So you have to read out that state. You have to read a spin state. So that is the readout scheme. So now if you look at any quantum computing architecture approach, whether it's atomic physics based or laser based or superconducting qubit based or semiconductor based, there are certain criteria the systems need to follow. Actually put forth by DiVincenzo in 1997, and these are the main criteria. There are a lot of some auxiliary criteria came up later. So the ability to address the qubits individually in a quantum dot that you can easily do by addressing this or activating the specific gate which is connected to that specific qubit. Initialize the individual qubit. This also you can do. Okay, I mean, we'll not go into detail how you do that, but our focus today will be on readout. Okay, and perform 1 and 2 qubit operation. You can do spin up, you can change spin down, or you can change the coupling, and you can do all these operations. This all can be done by voltage pulses, and read out the final state result of a single quantum measurement by using a single quantum measurement. That means you have to read out the spin state. Okay, you can do all the computation, but if you cannot read it out, there's no point. So this readout is actually probably one of the most important aspects. And that also you have to do with a single quantum measurement. That means very high accuracy. And you also have to read out these states very fast. For example, for error correction schemes, you probably need to also understand how the computation is progressing by putting some auxiliary readout schemes. Okay, so and this readout also need to be done very fast, much faster than the decoherence time. Okay, and almost in a non-demolishing way. Okay, so that means readout is probably one of the most important aspect. And interestingly, you have to read the spin, not the charge. That's the issue. So the question is, charge or spin? How do we read out a spin state of single electron? If you crunch the number, what you find out is the magnetic dipole moment that you can detect by flipping a single spin is very, very weak. You cannot detect it. It's really weak. At the same time, charge you can detect. Coulomb interaction is much more stronger, and you can detect Coulomb interaction or dipole moment change with this electric dipole moment change, which you can detect. But spin detection, or just spin is not easy. So the way it is accomplished is you do some process, some protocol to do a spin to charge conversion, and then you detect a charge. So you always detect the charge. You don't detect the spin directly. That is the way. So this talk now, I will now go into how you detect the charge or how you read out the charge state. Then how we convert this charge information into spin information. These are the two aspects we will try to cover. Okay. All right. So this is just a quick, recap 101 on gated quantum dot systems, because it's important to understand this, this process. Otherwise, we'll not be able to follow the technology, the details. So these are always defined by gating on two-dimensional systems. When it's a two-dimensional system, it could be a MOSFET kind of architecture where you have a thin layer of electrons confined at the interface between the silicon and silicon dioxide interface. Or it can be some kind of quantum well heterostructure. For example, this picture here shows a heterostructure consisting of gallium arsenide and aluminum gallium arsenide with a small dopant layer here. So because the band bending and band gap mismatch, you will have a small, very narrow quantum well at the interface. And this interface, if you engineer it properly, you will have only one level below the Fermi level. And that is going to be your two-dimensional system. So your starting point always for any kind of quantum dot qubit is a two-dimensional system. It could be a MOSFET, silicon dioxide two-dimensional system, or it could be one of these. Okay. The current state of art is the MOSFET and the silicon germanium. That's what most of the work is going on. But this is just giving you an example, just to give you an example. But a lot of progress in this community has been made on gallium arsenide, so we cannot ignore this topic. And still, a lot of work is going on. Okay, and it's a beautiful system. That's a system to work with. So gallium arsenide and aluminum gallium arsenide, you have a thin layer of electron. Then what you do, that is a starting point. Then you deposit by sample processing or lithography techniques, standard fabrication techniques, which involves both photolithography and electron beam lithography, nanoscale such gates, like you have like tens to hundreds of nanometer scale structures. That's what you do. And for example, if this is just a toy model. If I deposit this pattern and apply negative voltages on all these gates, I will get a confinement in the middle. So all the green region, I have electron. Because of the electrostatic or Coulomb repulsion or the gating effect, you will have you will have no electrons under these gates, the red color region, and effectively your conduction band landscape is going to look something like this, and there will be Fermi level will somewhere here, and you can have many levels underneath. Okay, and this is one of the most common architecture. More common geometry people use. Now people have moved on from this one, but this is very popular. If I use this gate scheme and apply voltages on all this gate, I will get some confinement, something like this, where this middle gate, of course, you have to play with the voltages here a bit. So the middle gate is going to split the large confined region into two. So you get a double quantum dot, an artificial molecule. That's what you are going to get. So this is basically the 2 qubit in a LD qubit architecture or a 1 qubit in a ST0 architecture, either one. Okay, so that's what it is. So now, if you look at what is the basic physics, because we need to understand a little bit of physics of this quantum dot to move further. So as I told, quantum dot is a small confined region which is connected to source and drain through tunnel barrier, which are represented by the small gaps here. And you can also apply gate voltages to this quantum dot and change its electrostatic potential. Okay, so there is source drain volt and there is a gate voltage, and there are discrete states because of the confinement, and you can change the position of this gate, the position of these levels by applying change the voltage on this gate, or that is the more. That is the most common way. So what you do is you apply voltage and you can have the levels aligned between the source and drain region. Whenever the level is between source and drain region, you get a peak in the current. Whenever there is no level, you get a gap. Okay, so there will be regular oscillations, okay, of current when I sweep the gate voltages, because I am pulling or pushing this ladder up or down, and these oscillations are actually called Coulomb blockade oscillations. That is, whenever there is no current, that means there is no level in between the window. And if there is something here, then there's a current, there's a peak. Okay. And so this phenomenon of not having any current is called Coulomb blockade. And if you delve into the details of that, this is actually not purely quantum mechanical. There is a classical side to it, because there is quantum dot is a small charged object, and you have Coulomb repulsion from the electrons already there on the island. So you need to overcome that Coulomb repulsion to put charge onto it, to run current through it. So that is why it's called Coulomb blockade oscillation. So you apply enough potential, enough gate voltages to offset that charge, then you get a current through it. And or you have to tilt your potential landscape, source drain landscape, much to include the levels. In either way, you can run a current through it. So usually what people show, or you would see on a paper, on a publication, or if you have to tell that you have a quantum dot, you have to show not only this one, you also have to show something like Coulomb diamond. It's a cartoon. I will show you the actual data in a minute. So this is actually a two-dimensional plot where you have source drain voltage on one side and you have gate voltage on the other side. So this is the gate voltage I was showing, the same axis, but I plotted now 90-degree rotated. So you will get diamond-shaped regions of no current flowing through. These regions are because of the same phenomena, Coulomb blockade. And these diamond-shaped regions are actually the touchstone phenomena in the transport property of quantum dot. And you have to show this diamond-shaped region, unless people will not believe that you have a quantum dot. This is a must to start with the quantum dot measurement. Now, sorry, 1 second. Yeah, my light goes off automatically. Yeah. Now, we an actual data. So you start with these are diamond shaped regions where no current flowing through. And this is the common dot, this is the gate pattern. And what you're doing is you are taking one of the gates, in this case, the left gate. We can do any of these gates, making more negative. So when you do that, what you're doing is you're pushing these levels up because they are making negative. The electronic charge is negative. So negative voltage, higher energy for electron. So you're pushing this level up. Okay. So you're pushing this level up one by one. And that is why you get the Coulomb blockade oscillation in a periodic oscillation. But now, and each of the diamond correspond to, a fixed number of electrons. So n minus 2, n minus 4, n minus 6, like that. Because this region, no current means the electron is confined inside dot. It's not number is not changing. And if you go to the next one, you have pushed one electron up because you push one level out of your window. That means you have one level less. That means one electron less. Okay. Then you go to n minus 1, n minus 2, and so on. And finally, you need to go to n minus. You need to go to last electron, the first electron. So that is where you want. That is what you are going to use as your qubit state, the spin state of that last electron. Okay. So you have to reach there. Usually, you start forming a quantum dot by applying voltage. You will have hundreds of electrons. Let's sometimes thousands of electrons. But you have to make this voltage negative to push these electrons out one by one and go to last electron. But the problem here is when you do that, you are also inadvertently making the tunnel barriers also thicker. So you start something like this, thinner tunnel barrier, but all these voltages couple each other. This negative voltage will affect the tunnel barrier here and the tunnel barrier here. So what happens eventually, you will not be able to measure any current. You can see overall the current level is going down. You will not be able to measure any current, just because the tunnel rates are slower. As I told, the same issue, because you're measuring the current here, not a charge, right? So the tunnel rates are slower and you're not able to measure the current, and you don't know what the state of the qubit. You have no idea how many electrons are here because you're not able to measure the current. So what happens is that when you go to lower electron number or few electron regime in the quantum dot, the tunnel barriers become so opaque and transport's almost immeasurable. You also need, that means you need to sense charge. You need to know whether charge is there or not, or how many electrons are there. So you need some kind of charge detection, not a current detection. So this is what I was saying. In the qubit measurement, you actually need charge detection, not a current detection. Then only you can sense how many electrons are there. Secondly, the qubit state is such electron confined. It's not an electron getting replaced by another electron. Current means you are replacing the electron by another electron, right? But then you lost the state. So you also don't want to do that. So eventually the charge measurement or charge sensing is the only way out. And that also you have to sense one electron. Okay. So now what that means is the rest of the talk, we discuss about charge measurement, not current measurement, and in a quantum dot. Okay. So if you look at the history of electrometers, the electrometers are what you use to measure the charge. In 1754, that is probably the first record I could find. So where you have a very silk, tiny, very light silk string with a dielectric material, and what happens is this a pith. It's a pith ball. It's material that's called a pith ball, and if you bring any charge object close by it, you get polarized, and this polarized, and it also will get attracted. Okay, so this will move. That's how you detect the charge. But it's very crude. Okay, later, couple of decades later, so there's something called gold leaf electroscope. So it actually has two leaves made of gold. It's enclosed in a bell jar, and there are some ground reference on either side. Then you bring a charge object. Basically, it will get charged and it will start repelling and it will move towards the ground. So this will actually open up. This V shape will open up. So that is how people sense the charge historically. And these equipments are still available. You can buy. I think it's still there on Amazon or in other online shopping sites. You can still buy these. These are available. You can also calibrate, but these are really, really crude. So I just want to, for our cultural enrichment, I just want to mention this. Okay. Now, if you actually look at the art of charge sensing, we have to look at the MOSFET. MOSFET is probably the classical charge sensor. and it's a cryogenic MOSFET, side gated one. So basically you have a conducting channel and you have two gates, and you are, just like a MOSFET operation, if whatever the gate signal, you get that will get amplified. That is the standard MOSFET operation. These are large objects, okay, because if you need large current, it should be larger. So these are very, very large, hundreds of micrometer size. Okay, these are not really compatible with the charge measurements that we are interested, where we are talking about sub-micrometer scale objects. When you have large objects, the issue is you have a large capacitance and these are high impedance. So you have RC time constant. That means this will be very slow. These equipments, these devices will be very slow also. First of all, these are large. Okay, and you also need fast operation, because if you look at you have to detect the charge much faster than decoherence time, or probably few orders faster than decoherence time, which are microseconds. So you need to megahertz to nanosecond, megahertz to gigahertz time operation to have a successful, charge readout scheme for error correction, protocols. Okay, so these are not suitable, and these are very large for obvious reasons. Okay, now if you look at the quantum dot itself is kind of a transistor, because it's a physics, we discuss Coulomb-Blocked oscillation. So when you change the gate voltage, you get a change in the current. But here, the change in the current happens when you go from n electron to n-1 electron. That means one electron get the full cycle of change. So these are also called single electron transistor, because one electron charge change. The gate voltage, this you can convert into charge axis by multiplying the capacitance of the gate here. So that will be CGVG, that is some Q, some charge. So a change in charge corresponds to one electronic charge, n to n-1, or n-1 to n-2, or one electron change. You get a huge change in the conductor, in current and conductance. So this is actually a magnified portion from here. So if a small charge change, this is actually the charge axis, remember, okay, this, even though I have put gate voltage, but it's actually charge axis. So if you have a small change in charge, you get a large change in the current. So you can actually detect charge using the quantum dot itself, not with another quantum dot, an auxiliary quantum dot. Okay, so basically that is what people do. And this is one kind of a charge sensor which is used in the readout of quantum dot, where what you do is you couple another quantum dot to quantum dot that you want to measure. So these are scalable objects, so you can make as many as you want. Of course, that will increase the complexity. Okay, and you can detect things like micro electron per root hertz. What this means is you can detect charge of 1/1,000,000th of an electron, because one electron charge will be coupled to various things, because the field lines will go in all the directions. So even 1/1,000,000th of that is sufficient for you to detect a change. Okay, so these are really, really sensitive electrometers, these quantum dots. So you can use quantum dot itself as a sensor. So there are a lot of works. This some of the there are a lot of recent works too. So in this case, I have this blue-shaped region and the red-shaped regions are the conducting channels, and these are gates. The golden color or yellow color region is a gate. When I apply voltage, I get one confined region here, another confined region here. So one of them I define as my quantum dot, which will be the qubit, and another region I define as my, intrinsic, I would say single electron transistor, SET. Okay, so I can sense the current through here, and I can get information of the charge state here. So for example, whenever the current is low, whenever the electron is in here, you have an extra charge here, current through this one is below. And when I have an extra electron, when this electron travels out, then this current will go up. So I will get a sharp change in the current in the sensor channel whenever an electron transition happens here. Transition means whenever an electron changes its position, like going from tunnels in or tunnel out of the dot, I get a change in the current here. So here, if you look at, the upper part is actually showing you the Coulomb-Blocked oscillation by directly measuring the current through here. The lower part here, the brown one, is actually the transmission through here. These are tuned separately, differently. Okay, so what we are saying is, even though I don't see any oscillations here, but I can still see that there are electrons going through the circuit. These are picked up by the sensor. That's exactly what I was saying, because even though in the pure electron regime, you will not be able to measure the direct current because of the thickness of the tunnel barrier and the reduced tunnel rate, but you can still measure the transport or the position of the electron state of the dot by looking at the sensor. So this is actually charge sensing. You're sensing the charge, you're sensing one electron. Okay, and these are separated by a few hundreds of, couple of hundred nanometers apart. Okay, so you basically what you do is, this is another example where I have an array of quantum dot. Each of this gate I have a quantum dot. This is simulation. This is an actual data, and I have another channel here on the bottom where I have few dots, which is for sensing. So in this case, they have basically just show this one. They have energized only one dot, and what they did is they pass the current through one of the sensor. Okay, and they can understand what the state of the dot nearby. So in this case, what they did is they swept the gate so that you are moving this level upwards, and watch the state of this sensor dot. So you are getting information of this one of the dot by watching sensor dot. Okay, so whenever the current is down, that means electron is in. In this state, the electron can randomly tunnel in or out, because the tunneling even is a quantum mechanical object. Actually, it has a probability to stay in and probability to go out. So what you're seeing here is most of the time the current is down. That means the electron is most of the time inside. But occasionally current jumps out. That means electron also jumps out occasionally, but immediately it goes back in. So the current goes back. But in this case, the electron is in resonance with the Fermi C here. That means equal probability of in or out. That means there's equal ups and downs in this current of the sensor. Here, if you go further, electron should be most of the time outside because the level inside dot is further up. But there are probabilities where this electron can tunnel in, but it will tunnel out faster. So that is what this sharp spike, downward spikes are. Okay, so what you're doing here is you are capturing the information literally in real time. You are actually getting information about where the electron is, whether it is inside or outside, how long it has stayed inside, how long it took the electron, how long it took for the electron to tunnel out. All this information you are actually inferring just by looking here. You are not doing any measurement here. You are actually looking at the sensor dot. So this is the art. This is the current state of the art. And I can actually also look at the occupation time, because this is a time axis, and from that I can look at what is the occupation statistics of the dot and as a function of the gate voltage. So when I do that, what I'm doing now is if I go from here to here up, I am actually sweeping through the Fermi level, and that's exactly what the occupation also should vary like, and that's what we are seeing. So the occupation also varying like the the Fermi function. From fitting the Fermi function, you can actually get the temperature of the system. So temperature of system is an important aspect, even though your system is probably cold. This experiment is probably done at 10 millikelvin, but electron is probably at 100 millikelvin, because at that temperature, you cannot cool down electron because of the lack of electron-phonon coupling. And so you have to, electron temperature will never be the temperature of the crystal. Electron will be completely, decoupled from the crystal at that temperature. So this is one of the way you can measure the temperature of the electron, which is very important parameter, because you need to have the thermal energy of electron far less than the other energy you're discussing, like the tunnel coupling energy or single particle states or Zeeman splitting. All these things should be much larger than thermal energy. So it's important to know how cold your electrons are, which is actually an issue whenever we work with any of the system. Getting the electrons cold is probably one of the most difficult challenge. Okay, now this is what it is. This is how you use quantum dot itself to measure. So you just make few extra bits of quantum dot. Okay. Now let me quickly show you another device. That is something called quantum point contact. This is another device where you have one gate. You don't have a full quantum dot. You just have one extra gate. Okay. So when I apply negative voltage to these two, and all of these actually, then I will get a thin channel here. Okay. And that channel is actually a quantum channel, it's a quantum wire, where the modes of transport are actually quantized. And this quantized mode will give you quantized conductance, like shown here on the right. This is actually quantum point contact, and this conductance will be quantized into E square by H. And there is a very detailed, beautiful theory by Landor and Butiker, which I am not going to go into detail. But what you need to understand here is when you apply voltages, I'll get some kind of parabolic confinement, and the energetics of the electrons will be defined by this equation. And the transport is quantized, and there are between these plateaus, I have very sharp, feature in gate voltage, the sharp feature and the conductance against gate voltage. So here also, this just like the Coulomb side of the Coulomb blocked oscillation, these features also I can use for sensing. Okay, so the advantage here is you have only one gate. Okay, you don't have many gates. You don't have to form a quantum dot. You just need to form a constriction. This is a very attractive candidate for sensing. Okay, so that basically this dates back 1993, where this is a quantum dot, and you have an extra gate here. The current through this constriction is actually measured, and correspondingly every Coulomb blockade oscillation through the dot, you can see a small change in the conduction of this channel because of the capacity coupling of the electron staying here to this channel. You get a small change in the conductance, and this is another example. Okay. And this one, this change. But when you go from n to n plus 1, n minus 10, you get a small change. This you can use to detect the change in the charge or dot occupation, change the charge to the dot. But again, this is another example where you can measure the direct current, but as I told, the current will be very, very low when you go to higher negative voltages because of the tunnel barrier gets really thick. But still, your current from the sensor, that is the red color here, that is this conductance sensor, that's red color here, through this channel, that is very strong. So you can use this to read out the state. That's what you have to do. There's no other option. But again, this is just a direct current measurement. What that means is kind of a very slow measurement, because you are still measuring the current through an impedance device, which is very, very high in resistance. Like these are like hundreds of kilo ohms to mega ohm range, and this is located, somewhere inside the cryostat. And you're still measuring a current through a current averaged, some kind of preamplifier. So this is still slow. So how slow this is, we just look at it. So I can park my device here. So that's correspond to this configuration of the dot, because you are going from one charge to other charge state. So here both charge states should have the same energy. And this electron will tunnel back and forth. That should give me, abrupt changes in the conduction of the channel on the side here. And this looks like some random telegraph signal. So whenever the current is low, electron is out. Whenever the current is electron is in. Whenever the current is high, electron is out. So I can get where the electron is by looking at the current state of the sensor. And this is also kind of a very slow measurement. And because this is again done, you are measuring the direct current from the device. Okay. So I'm going to skip this slide a bit and just tell you that this measurement has a time resolution of 1 millisecond, but you need these measurements done much, much faster. So we have to basically go to some other technology where we want to measure the charge state really, really fast. Okay, that I will discuss how we are going to do that just by filling a small bit of information. That is, we have been measuring so far the charge, because I don't want to miss this point, even if you run out of time. So let me tell you how we are going to measure the spin. But so far we have been measuring the charge only, charge of the quantum dot. But we have to measure the spin. So how do we measure it? Let me fill that information first. Then we will discuss how can we improve the the readout speed of these devices. Okay. So here in this device, of course, you are actually going to form a confined region of electrons or the quantum dot by applying voltage to all those gate. And I can roughly think the confinement is something like this. And when you put the last electron and apply a magnetic field, I'll have either upstate or downstate. Okay, depending upon the G factor of the material, one of this will be higher energy, one of this will be lower energy. And if I can actually slide the state compared to Fermi level using gate voltage pulses applied to one of these gates, say labeled P. So if I put a pulse in such a way that this state is up, this state is down, I mean, this state is below the Fermi level, then I can have this electron tunnel out. Okay. If I get and this charge sensor on the side, which is a channel, is a quantum point contact, that measures a tunnel out event, a charge, occupational change event in this current. That means I have downspin. So that I have measured a downspin now. If I don't measure anything, that means I have an upspin. But how do I confirm I have an upspin? I up the pulse again a bit, such that this level is also above the Fermi level. Then I get a tunnel out signal. So you are actually measuring only the charge state of the dot. Not measuring in spin, but what you're getting is a spin information. Okay, the spin is down. In this case, the spin is down. If I go to this state, this gate voltage by applying a pulse, if I get a tunnel out event, that means if I get a change in the current here, that means I have a downspin. If I don't get it, I go further up. Then if I get a tunnel out event, I have upspin. So these are the two situations I want to bring into the pulse sequence, and you can check, you can read the spin state of the quantum dot. So for example, what I will do here, the pulse sequence here, I will make the pulse, very negative. Say 0 is just a reference number, so that both states are above the Fermi level. So you are emptying the dot. That means you're initializing it. Okay. So, okay. Now what you can do is I can fill it. I can make the voltage positive. That means I can bring the both levels down. So I will fill this dot. Of course, these are single electron devices. Only one electron can go at a time. Either this up state will be filled or the down state will be filled. One of the state will be filled. And your job is to detect which is filled. Okay. So for that, what you do is you go to a pulse which is halfway through, so that this state is out, this state is in. The inside the dot, this is outside. So if I measure a small change signal here, that means I have this tunneling event. If I don't measure, that means I have upspin. Okay, this is an actual data, and you can see this is going to follow the same sequence. But in this case, you are seeing a small blip, a signal here that correspond to this tunneling event downspin. So this is the pulse sequence that you would use to measure the spin state in a single dot or the LD qubit. So that is basically called energy selective readout, because you are actually, by changing the energy level of the dot, and you are selecting the energy level which the electron is occupying, and you are forcing that level to tunnel out, that electron to tunnel out. So this is actually called energy selective readout, or also called Elsterman readout, because that is, he is the one who came up with this idea first. So this is one way to read the state. Okay. There is also another way, which is a lot more actually now popular. This is actually something called spin blockade based readout. Okay. So this is generally applicable to a double dot. Okay, double quantum dot or artificial molecule. When I say double quantum dot, this is operated in a 1-1 or 0-2 charge state regime. That means either you have one electron in each dot. That's the state, because that can be in a single state or a triple state. And you can tilt the landscape by a voltage, and you can push one of the electron to the other dot and go to 0-2 state. Okay, that's the idea. You can take one electron and push it to the other side by tilting using the potential, one of the voltages here. Okay, so now if you look at the energetics here, I have one electron here and one electron here. Okay, so if I have one electron in each dot, that actually can be in a single state, 1-1 single state, or a 1-1 triple state. Remember, 1-1 single state and 1-1 triple states are very close in energy. I mean, the splitting between these two are very, very small. That's only tunnel coupling. So if this is in the 1-1, if the dot is, we want to know whether this spin is up or down. That's our aim. Okay. What we'll do is, we will try to run a current through it. Okay. You can measure the current, but still you have to sense this transition using a sensor. But you apply a bias so that this electron will travel from the lead to here. This electron could be spin up or spin down. You want to know what is this. Okay. So if it is spin down, is this spin up, then this actually in a single state, S11 state. This single state can go here. This is within this window. But if this was spin up, this need to go the triple state of here, 2-0 triple. That is the triple state of a single dot. That's much further in energy. This is an orbit, this is a different orbital state. So because it's energetically, it's 2 electrons and 1 dot. That's the second orbital. Okay. In this case, this cannot go here because of this at higher energy. So this will get stuck here. What that means, this electron will not tunnel here. So just come, that is this situation, triple state. Okay, now if we come back to this diagram here, I have state. If I tilt the landscape, this electron can go here, and my sensor here will measure a current, measure a transition. At the same time, if I have this state, if I tilt the landscape, this cannot go here, 0 to cannot go here, because that 0 to state is high up in energy. So this electron will stay here itself, and the sensor will not measure any event. So we can use the Pauli exclusion principle, this based on Pauli exclusion principle, to read the spin state. So this is also called spin blockade, readout technique, where you are looking at the possibility of transition, from the into a single to triplet state, and that you are detecting by measuring the current through a charge sensor. Okay, so these are the two ways you actually, because you are always measuring the charge state, you are not measuring the spin. But these are two ways you are actually measuring the spin by measuring the charge. Okay. Now, how much time I have, Shika?
You can continue, no issues.
Okay, I'll take another 15 minutes, 10 to 10 minutes more. Is that okay?
No problem, sir.
Okay. So thank you. So let me actually go a little bit on the work that we do currently. Okay. So on detecting the charge much faster. If you look at the slide so far, we're all measuring in seconds to milliseconds, time scale. But as I told, you have to measure it much faster. The intrinsic bandwidth of all these devices, whether it is a QPC or singleton transistor, most of these are in gigahertz or terahertz. Okay, because they are devices with a very small capacitance. The capacitance define the bandwidth eventually, right? So it's an RC time constant. It's very small capacitance. They are autofarads capacitance. If you look at these are autofarad to femtofarad range. Okay, so these are intrinsic. So intrinsic bandwidth is actually very large. For QPC, it's actually in terahertz. Okay. What happens is, this is a picture of the system. So you have devices somewhere here connected through all kinds of cables and wires. And this is like a couple of meters of cables. Cabling is already here. Then another maybe couple of meters connected to all the equipments, all the electrical measurement unit. So what we are seeing is our measurement is eventually marked by the RC time constant of the circuit. Okay. So what we have is like a mega ohm, hundreds of kilo to mega ohm range impedance here, and you have nanofarads of capacitance contributing from the wire. So that's actually limiting your operation to kilohertz range. That's what is happening here. Because this is nothing but a power transfer theorem. That's you're not getting the signal out or in the fastest way, even though the device is responding, but you are not able to read it because of your electronics. So what you need is some kind of impedance transformer. Okay, so you need some kind of impedance transformer to transform the high impedance of this quantum dot or the QPC, this sensor, to 50 ohm. Okay, so this is accomplished by using some kind of a tank circuit, which is actually superconducting also in nature. This is a circuit representation. So there is an inductor and there is a capacitor. Capacitor is generally defined by the pad itself. And there is devices nearby. Of course, there are wires, bonding pads and other thing running around, but those are not shown here. So this circuit will have a resonance defined by the inductance and capacitance here. Okay, this C and this L. And this is a bias T which will allow you to apply both AC and this AC and DC. Okay, so now once again. Okay, now this resonance, the Q value or the reflection from here depends upon, you run through all this formula, it depends upon the RD is the resistance of your device. This is what you are trying to sense. Okay. Because the resistance of your device, the device is your sensor here, not the quantum dot. Your sensor. This could be a device, not a qubit. Okay. Device is either sensor quantum dot or the QPC or the quantum point contact, whichever you are using as a sensor. That's a high impedance device. And whatever the small change in its conduction is basically proportional to this change in its resistance or impedance. Okay. So now, if you work out this formula, what you will see is at resonance, the reflection is actually a strong function of the resistance of the device. So what you do is you don't measure now the current through device at all. You just look at, you pump RF into the sensor and measure only the reflected power, S11. That's all you do. You can do S21 also, but to reduce the number of cables, we generally do only S11. Okay. To use the directional coupler somewhere else, and you measure only S11. So the S11 will look like something like this, and this height or this depth will depend on the state of the device. And so you can know what is advantage. The advantage is you can set this measurement frequency whichever way you want by choosing appropriate L and C. And you have transformed this impedance if you follow through this equation. Then you can measure the change in the impedance of the device at a time scale which is prescribed by this tank circuit. That's what it is. Okay. Now, what that means is your reflected power will be amplitude modulated by the change in the resistance. That's what is going to happen eventually. You are actually sending an RF signal, and you are measuring the reflected one. The amplitude of the reflected power should depend upon this change in this impedance. That's what this technology is about. This is called radio frequency operation. This is used left and right in this quantum dot qubit technology. Okay. Now, in 2003, this was what is done is they use this technology to measure the charge transport in microsecond time scale. So again, it's ups and down, but what you're doing is you're measuring some voltage, RF voltage, is a sensor voltage. Okay. Sensor is another quantum dot sitting on top of the quantum dot. There's two quantum dots here. You see this weird shape region that says superconducting quantum dot, which generally people also call SET, single electron transistor, because sensor, so people call it a transistor. But the actual the qubit or the actual quantum dot they are trying to measure is under because it's at the interface between in the quantum well. So you put another quantum dot on top of it, and you are measuring the reflected power from this device, and that's going to be up or down depending on the charge state. And you can actually measure currents as low as something like a few femtoamps or even less than a femtoamp using this. Okay. That means if you look at femtoamp, that is like less than 10 kilohertz of tunnel rate. So you remember, you cannot measure any current below 10 femtoamp. So you can measure less than femtoamp. And so that is one of, because it's very, very sensitive. Number one, it's really sensitive. Second thing is it's very fast also. You can get a really fast information about the tunnel rates of the system, tunnel rates and dot occupation and everything. And there is also another work where obtained this 1 microelectron per root hertz sensitivity using the similar technology. Then this was operated for Kelvin, because of course this actually there's not very different from here. The main thing is they did some trick in the lithography and they were able to go to very, very small size, and they were able to operate this device at a higher temperature. Okay. Now, similar thing you can also do with the quantum point contact, because this technology is same. Again, you actually connect this channel to the similar tank circuit, and there is a resonance here. Here they operate a much lower frequency. I'll tell you why the reasons are, and that's something which our current focus is. So depending upon the resistance or conductance of this channel, the reflected power will change. This is S11. Okay, and from that reflected power, you can demodulate the signal, and you can obtain the charge state of the dot. And this honeycomb-looking diagram is a signature of a double quantum dot, and they were able to map it looking at the reflected RF power. That's all they did. Okay, this is differentiated RF power, RF voltage as a function of the gate voltage. That's what they are plotting, and they can map the same thing really, really fast. Usually, this diagram will take at least overnight. But they are able to do it in less than 3 minutes. They were able to get all this information. So it's a very, very fast, sensing, actually. It's a technique. Okay. Now, if you look at the technology, what we discussed so far, this will have, hundreds of thousands of, quantum dots. And to read out the state, you actually would need a sensor per quantum dot. That means you need additional quantum dot or additional QPC as the number of the qubit. But that is actually an issue. There's a lot of issue in terms of the real estate design, gating schemes. All these things actually gets very complicated. So recently, what people started doing is they connect one of these to similar technology, RF electrometry, whatever we discussed so far. Then what happens is the reflected power, the resonance, the Q of the resonance, actually, the reflected power will change. The phase and amplitude of the reflected power will change depending upon the charge state here. So it's not about the charge states. Actually, this is the energetics of the dot. When the electron is not tunneling out, that means you are somewhere here in the landscape. The electron tunnel out, that means you are somewhere here. So when the electron is not tunneling in or out, is stable inside, that means the reflected power will not change. The moment there is a transition, if you are in this gate voltage range, that means electron can tunnel in or out, then RF power that you apply can drive this transition. You are actually kind of probing it. Okay, you can drive this transition, and it's a very small power. Okay, drive this. You are not going to decohere it, and you also have to make sure that this frequency that you are applying is not the qubit frequency. Otherwise, it will drive that you don't want to drive out. You just want to drive this transition. Okay, probe this whether this electron can tunnel in or out. That's what you're probing with this one. That actually will bring a phase change, the reflected power, because the change in the quantum capacitance or quantum admittance of the device. Because the quantum admittance will change. Then what happens is the phase will shift. So what we are looking at is the phase change delta phi as a function. And you can see this is the signal which is captured by the QPC here, which actually is saying there's a charge transition here, there's a charge transition here, but same information actually captured by the sensor also. But now what you have done is a fabulous thing, because you have not add any extra device to sense, because if you ignore this part, it's only to standardize this technology. There's nothing. You can just use the dot gate system itself sense. So this kind of architecture, that's what in the near future you are going to see, where each of this gate you can connect to one of this tank circuit, and you can directly measure the occupation of the dot. Okay, so that's the idea. This is the latest state of art. Okay, and now let me also spend 2 slides on what we are also doing. So this is the latest paper which published like a few weeks before. So this is a technology where something called step impedance matching circuit, where you are connecting to one of this sensor, and the advantage here is you can actually impedance match to any high impedance. Usually, if you look at the lambda-terminal LC circuits that we discussed so far, they have self-capacitance, and there is a limit how high it can go into frequency because of self-resonant frequency of the inductor. Okay, and plus getting impedance matching high impedance load is also not very easy because of the same reason. So these things will allow you to impedance match to very high impedance devices. For example, quantum dots can be very much higher in impedance compared to the QPC, because there's only one junction here, there are 2 junctions there. Okay, and this is actually showing you the signal to noise ratio as a function of this where you bias it, and this is all normal standardization measurements. And what you're seeing is the amplitude modulation, what discussed. So far, what we are looking at is in the time domain. Now this is in the frequency domain. So you can see a signal, whatever you apply, a small signal here is picked up by the reflected power. Okay. Now you can also get information about the quantum capacitance, because that is what you can get from the phase of the reflected power. That also varies in a quantized manner. This is a quantum capacitance that you are measuring of the one-dimensional channel. That also in a much faster time scale. So this is one work. And another work, what we do is, we have done is, we couple these devices to resonators in a circuit QED fashion. What you have is, you have a resonator on a surface, that is a coplanar waveguide geometry. Okay, just like you have normal atom, you can couple to a laser cavity. You are coupling an artificial atom to a microwave cavity. That's the idea here. The important point here is the frequency of operation is decided by the geometry. So you can control geometry by control, and you can control the frequency. You are not limited by the self-resonant frequency of a lambda element in this case. And this is in this work where we have coupled a superconducting cavity to a quantum point contact, and these are simulations and these are resonance of the cavity. And we chose to operate at this frequency lambda, that's around 3.4 gigahertz. So that's much faster than anything that has been operated so far. Okay, and we are able to get a very broadband amplification, charge amplification. This is sensitivity. This is actually plotted in terms of the conductance quantum, but this is actually charge sensitivity. And we can operate, with a few nanosecond, couple of nanosecond, rise time with a sensitivity of 0.15 micro conductance quantum per root hertz. And if you convert in actual unit, it will be 12 picosiemens per root hertz. That much change we can detect, okay, in this one. And another important fact, this is probably the last penultimate slide. Another important factor is we are talking about a quantum sensor. Okay, when we talk about quantum sensor, any quantum measurement will have its own back action, just like the microscope. Okay, or just like the Heisenberg microscope. So if you look at this is the amplifier noise, and this is the noise of our device. Our device noise actually exceeds the amplifier noise. And what is the reason for this noise? You can think of like there could be classical noise, there could be quantum noise. But in this case, what we see is we are actually limited by the fundamental quantum mechanics here itself. That is a quantum limit. We are actually approaching the quantum limit. So the quantum noise, these are tunneling devices, electron tunneling transport, right? That means there should be a stochastic noise, or it's also called partition noise, coming from the device because of tunneling events. So the tunneling events is like you're actually shooting a bullet. There's a randomness to it. Okay, that's a quantum mechanical randomness, fundamental randomness. This is exactly what you want to use for random number generator. Okay, same thing. Okay, so this is a pure randomness which is not available classically. Okay, because of that there is a noise to it. Okay, that noise is what we are seeing. The way we can check it is, if there is no transport, the noise should be zero. The transport, if the transport is actually reflectionless, what that means is the transmission is 1. Then also there shouldn't be noise. That's what we are seeing here. We can look at how much power is there in the noise, and you can characterize the noise. And we see that this noise is completely due to the electron tunneling event or quantum mechanical, and this follows this expression for partition noise. And another signature is, if it is a tunneling noise, it's actually a short noise. It's called short noise. Short noise will have a square root of the power dependence, whereas the signal will have the power dependence, and that's what we are seeing here also. These are two touchstone phenomena of a quantum noise. So what we are saying is we are limited by the quantum noise, and we are almost at this edge now. Okay. Now, other thing, when you have quantum noise, the issue is it's going to backact on the system. There will be back action. Okay. Just like if you measure momentum, it will change the position. You try to measure the position, it will basically disturb the momentum. Something like this also is going to be back action. That's the other side of the coin of quantum mechanics. Okay. So now what we are seeing in this case is these tunneling events can perturb and induce the vibrational modes in the host crystal, because this is a gallium arsenide crystal. This is piezoelectric. Tunneling noise is electric. So this actually can do mechanical noise, mechanical back action. Okay, this electromechanical back action. That's what we are seeing, and we can also, that is going to put certain peaks in the reflected power. These peaks correspond to mechanical modes, and by analyzing these peaks from the signal noise ratio, these peaks which are actually generated by noise. Okay, it's kind of an oxymoron statement. You are getting a signal from noise. Okay, here that's what it is. That's what's happening. I mean, the details are here. So, but I will stop after this. So from that, you can look at how much the strain is there on this crystal, and you can use it for displacement sensing. Okay, we can get a sensitive picometer, which is a really good sensor per root hertz, with a bandwidth of in a nanosecond rise time, or in this measurement band. So you can measure the small fluxing of the crystal, the picometer scale, using this technology. So this is the landmark paper from Heisenberg in German. Okay, this is about uncertainty. And as far as electrical amplifier is concerned, this is the limit where the voltage noise spectral density into current noise spectral density should be h bar omega by 2, where omega is your measurement bandwidth. Okay, so measurement frequency. So this is a noise energy. So this is actually conserved. That means you cannot beat that limit. So what we see is we are seeing the short noise, and we have to analyze further and look at how close we are to this limit. That is our next step. And by saying this, let me thank again the organizers, and I'm now open. I'm ready to take questions. Thank you.
Thank you so much for presenting the session. There are a few presenters have a few questions. So if you allow them to please ask. Hello.
Yeah, I can hear.
Yes, sir. There's a few candidates have some questions, so they want to ask something. So please, if you can answer the questions.
Yeah, sure. Shall I keep the screen shared, right? Or
Sir, there are only few questions I can read out for you.
okay.
So the first question is from Miss Anjana. So how her question is regarding how is such a low temperature physically implemented then?
Oh, very good question. Okay, let me go to the slide. Okay, I might have some picture somewhere here. Yeah. So this is a picture of a equipment. It's called dilution refrigerator. It's located in our lab. So of course, this is the inside of it. When it is working, everything will be covered up like a Russian door. So you have multiple vacuum containers to avoid all kinds of radiation going in, because even any microwave, any IR photon matters for us, because that will heat up the sample. Sample goes somewhere here, and there is something called there is a technology which is called helium-3 and helium-4. These both are quantum liquids at temperature. So there is something called dilution refrigeration, where you are actually pumping on helium-3, which is in the helium-4 matrix, or helium-4 phase. So you can get continuous cooling because it's a recirculating system. So you pump helium-3 from one side and you put back another side. Okay, it's a complicated system actually. So, but this is called dilution refrigeration, and you can keep the sample area cold down to few millikelvin, like a 6 to 7 millikelvin range. But the moment you add electronics, and still warm up to bit, like maybe 10 to 20 millikelvin will go up when you add all these things. But as I told, it doesn't really matter, because what you are really worried about electron temperature, which is never to that time. It's always in the 50 millikelvin, 100 millikelvin range. Okay, so you use something called dilution refrigeration, and you talk to sample using this high frequency and DC wires, which is located somewhere down here. Sample is located somewhere down here.
Thank you, sir. Another question is again from Lilith Kumar. So his question is how we can voltage to the nano level, means atomic level structure, to see the electron behavior.
So very good. I think this is question on the fabrication, most likely, I guess. So these devices, let's go to some device here. So if you look at it's an older device, this is even not really that small, but is there something else I can show? Let me check. Yeah, this is device. If you look at the whole scale bar, you see it's only 300 nanometer. That is this whole dot size approximately 300 nanometer, and these are 50 nanometer size. This one. So these are actually done by a technique called electron beam lithography. Okay, so we use electron beam to pattern the substrate using some resist, and it's just like photolithography is done by UV light, but electron beam lithography is by beam of electrons, which you can actually define structures down to 20 nanometer. and you apply voltages to these gates, and you can confine electrons to a certain region. That is the technology. That's what you do.
Yes. So another question is from Anjana again. Her question is regarding any basic paper or resources to better understanding this topic.
It's all there on the slide. All the papers is actually there on the slide, or each slide has a reference. So whatever I have discussed is there on the slide. Actually, if you, I assume that this talk is probably recorded. Is that true? Then it should be there on the slide, or you can write to me. My email is just madhu@isertvm.ac.in. That we can always share the paper. But all the papers are on the slide. It's references are on the slide.
Another question is from Mr. Ashutosh Singh. His question is regarding the readout. So there were some spike in the beginning of the teeth hold, whereas in the plot of left it was a flat top. Could you clarify on this experimental and theoretical plot discrepancy?
I assume this is probably the slide. I mean, this is probably he was referring to. There is no discrepancy here. So, 1 second, sorry. What is my slide? Okay. Yeah. So there's no discrepancy here. So this is just like what is supposed to do in case if the spin is down, then there will be tunneling out event. The spin is up, there will not be any tunneling out event. So this spin is up. That means there is no tunneling out event. That means this is flat. Spin is down, this corresponds to this situation, then there's a tunneling out event. So now it tunnels out, but I think what I understand what he was referring to is why this is again coming down. That's why it's called a spike. So the reason for that is when this electron tunnels out, the dot is empty to receive an electron. So automatically another electron will tunnel into this state. So that means it's come down again. So there is this tunnel spin. This will tunnel out, but naturally this will get filled back by a upspin because this is available here. The states only electron is only here, right? Either here or here. Two electron cannot be there. There's only one electron. If the electron is here, for example, the electron is here. It tunnels out, but this state is now can receive an electron, so it will tunnel here. That means because you are sensing charge, so you'll sense this part also. That's why it's coming down. I think that is the question.
Thanks, sir. So another question is from Gururaj. So he's asking regarding the in PT symmetry, spin polarized current produced in quantum for the application of memory stores. Is it possible to apply spin system with quantum computing?
Basically, it's not about the spin polarized current. That is important if you want to transfer spin information from one place to other place. For example, you have a spin state defined and you want to transfer that information to a distant place. Then you can do that. But actually here you have to rotate the spin. That is the computational process, actually rotation of the spin. Whether it's a singlet triplet or whether it is a LD qubit, you have to rotate the spin. So it's not about spin polarized current that you probably need to transfer spin information to distant places. Okay, but not to do the computation.
So we take the last question. So is the Miss Shorish is asking regarding please suggest any book or resources for this quantum dot qubits.
I think the qubit books are I don't know whether there's a qubit, it's exclusive for qubit, but there are a lot of reviews on qubit, which I don't remember the actual the reference, but there are reviews by Vanderbilt on double quantum dots, in reviews of modern physics. There are reviews on silicon quantum dots, by Mark Erickson and also by Hansen. There are people a lot of reviews are available. As such, I don't remember there is any specific well-regarded book on quantum dot qubits. There are, of course, there are quantum computation books are there, but nothing. I don't think anything available for this topic, specifically for this topic. There are only reviews.
Okay, I think sir is able to handle all the questions now. As we come to the end of today's webinar, I want to express my heartfelt gratitude to each and every one of you for being a part of this enriching and insightful session. And I hope you found our discussion on charge and spin readout techniques in quantum dot qubits to be informative and valuable. A sincere thanks to our esteemed guest speaker, Dr. Madhu Thalakulam, for sharing their expertise and wisdom with us today. So remember that the learning doesn't stop here. I encourage you to take the knowledge you have gained today and apply it to your personal and professional endeavors. If you have any further questions or need additional information, please don't hesitate to write to us at quantumoutreachblr@cdac.in, which is mentioned in the chat box. And before we bid farewell, I would like to remind you to fill out the post-webinar survey, which is posted in the chat. And your feedback is valuable for us to improve our further webinars. Once again, thank you all for joining us. Your participation and enthusiasm have made this webinar a success. We look forward to having you with us our future events. Wishing you all the wonderful day, and until next time, take care and stay inspired. Thank you.